Physical properties of ethers. See, we know that ethers are colorless liquids, volatile liquids, because their boiling points are not very higher. So they are colorless volatile liquids. Let us discuss their boiling points. What we need to know is, since these ethers are not linear and they don't have any OH bond, they cannot form, there is no H bonding in these compounds like corresponding to their isomeric compounds like alcohols. So their boiling points are like more than alkanes, but it's less than what? Alcohols. The reason being they are polar, so it is more than the normal alkanes, corresponding alkanes, but since they have no hydrogen bonding, it is less than alcohols. That's the most important thing about the ethers is. Then let us discuss their solubility. Now what you need to know about their solubility is that since they can't form hydrogen bonding except what? Dimethyl ether and methyl ethyl ether, rest of all ethers are, all other ethers are insoluble in water because no H bonding. Since the oxygen doesn't have any H and there's a large angle strain, there's torsional, the steric hindrance being created by the alkyl groups, no hydrogen bonding is possible. So except these two, the ethers are insoluble or they are not miscible with the water. Now let us see the chemical properties of ethers. The most important chemical reaction of the ethers is the cleavage of the CO bond in the ethers. It's the basically is done by reaction with halogen acids. So like alcohols, they also form what? Alkyl halides. What you need to know is, if we have any symmetrical ether with HX, it is going to give us what? One alcohol and one alkyl halide. So it's a very simple reaction. Like if we have diethyl ether reacted with HBr, we will get ethanol and we will get what? Ethyl bromide. See, what we need to know is that the reaction of course, the halogen acids will be in this order because their reactivity is in this order. But let us see what happens in case of what? Unsymmetrical ethers. Like if we have this one, ethyl isopropyl ether, and when we treat this with suppose HI, what you need to remember is that this reaction again is being allowed to carry out only by SN2 mechanism, and the protonation of this oxygen takes place. This results, this reaction is going to give us what? Isopropyl alcohol and ethyl bromide. So the question comes is, this CO bond breaks, this doesn't breaks. Why? Because we have to remember the reaction goes by what? Like let me tell you the simple mechanism. What happens is the acid releases H plus ion, so the protonation of this oxygen takes place. Now what happens is this oxygen acquires a positive charge. It has to withdraw electrons from any of the alkyl chains. So from where it will withdraw? It will withdraw from that alkyl group which is giving it what? Less plus I effect. So it is withdrawn from this side, and therefore the iodide shows nucleophilic reaction on this one, and that is why we get what? The product like this isopropyl alcohol and ethyl what? If we have suppose ethyl iodide. So this is how the reaction proceeds. But remember, if we have in unsymmetrical ethers, an ether like this on reaction with HI, since now one of the part is a tertiary chain, this will on its own will go out, and therefore the reaction it goes out by SN1 reaction, and therefore the product obtained is different. What we get is this third butyl iodide and we get ethanol. That is what you need to remember. Now this oxygen CO bond breaks because the reaction goes out by SN1. It results in the formation of this tertiary carbocation on its own, where nucleophilic substitution takes place of iodide ion, and this is how we get this. So that's the most important thing about this one is. Now let us see in case of aromatic ether what happens in case of aromatic ethers. In case of aromatic ethers, of course, like we know in case of any sol, what we have is when reacted with HBr, we can easily imagine always, since this O will be having a partial double bond character due to plus R, always what we will get is this phenol and methyl bromide. Never, the reaction never goes in the other way around because we cannot break this CO bond because of the partial double bond character due to plus R effect. Second most important reaction of the ethers is the electrophilic substitution reactions. What you need to know in this case is that this ether group, I'm putting it R, shows what releases electron towards benzene ring, and therefore we can have then again further resonating structures. So it shows plus R effect, therefore it is ortho-para directing, and what happens is it will be what ring activating group. It will be regarded as ring activating group because it is increasing electron density on the benzene ring. Let us see how it shows these reactions. First, let us see the halogenation. Like let us take any sol. We are doing halogenation. So when it is treated with bromine, what we get is ortho as well as para substituted product. Para 1 will be the major one, so it will be para bromo anisol. That's the one thing. Now let us see the second electrophilic substitution. Nitration. Anisol on reaction with nitric acid, which is done in presence of sulfuric acid, forms ortho as well as para product. The para one will be the major one called para nitro anisol. Then let us see the Friedel-Crafts reactions. The first one is alkylation. In alkylation, what we do is we treat this with methyl chloride in presence of anhydrous aluminium chloride. Now what happens is orthomethyl and paramethyl substitution takes place. Para 1 due to what we have is it will be HCl. So para 1 due to symmetry will be the major product. Then let us see the Friedel-Crafts acylation. Anisol on reaction with acetyl chloride in presence of aluminium chloride results in the formation of ortho and para substituted product. We can call this as para methoxyacetophenone, and this will be the major product. So this is how what we can do is the Friedel-Crafts alkylation and acylation of the aromatic ethers.